The rate law or rate equation for a chemical reaction is an equation that links the reaction rate with concentrations or pressures of reactants and constant parameters. For many reactions, the rate is given by a power law such as where A and B express the concentration of the species A and B, respectively. The exponents x and y are the partial reaction orders and must be determined experimentally. They are often not equal to the stoichiometric coefficients. The constant K is the rate coefficient or rate constant of the reaction. The value of this coefficient K may depend on conditions such as temperature, ionic strength, surface area of an adsorbent or light irradiation. For elementary reactions, which consist of a single step, the order equals the molecularity as predicted by collision theory. For example, a bimolecular elementary reaction A plus B products will be second order overall and first order in each reactant, with rate equation. For multi-step reactions, the order of each step equals the molecularity, but this is not generally true for the overall rate. The rate equation of a reaction with an assumed multi-step mechanism can often be derived theoretically using quasi-steady-state assumptions from the underlying elementary reactions, and compared with the experimental rate equation as a test of the assumed mechanism. The equation may involve a fractional order, and may depend on the concentration of an intermediate species. The rate equation is a differential equation, and it can be integrated to obtain an integrated rate equation that links concentrations of reactants or products with time. Zero-order reactions. A zero-order reaction has a rate that is independent of the concentration of the reactant. Increasing the concentration of the reacting species will not speed up the rate of the reaction, i.e., the amount of substance reacted is proportional to the time. Zero-order reactions are typically found when a material that is required for the reaction to proceed, such as a surface or a catalyst, is saturated by the reactants. The rate law for a zero-order reaction is where R is the reaction rate and K is the reaction rate coefficient with units of concentration or time. If, and only if, this zeroth-order reaction 1 occurs in a closed system, 2 there is no net buildup of intermediates, and 3 there are no other reactions occurring, it can be shown by solving a mass balance equation for the system that, if this differential equation is integrated, it gives an equation often called the integrated zero-order rate law, where represents the concentration of the chemical of interest at a particular time, and represents the initial concentration. A reaction is zero-order if concentration data are plotted versus time and the result is a straight line. A plot of versus time t gives a straight line with a slope of. The half-life of a reaction describes the time needed for half of the reactant to be depleted. For a zero-order reaction, a half-life is given by example of a zero-order reaction reversed Haber process. The order of a reaction cannot be deduced from the chemical equation of the reaction. First-order reactions. A first-order reaction depends on the concentration of only one reactant. Other reactants can be present, but each will be zero-order. The rate law for a reaction that is first-order with respect to a reactant A is K is the first-order rate constant, which has units of 1 per second. The integrated first-order rate law is a plot of versus time t gives a straight line with a slope of. The half-life of a first-order reaction is independent of the starting concentration and is given by examples of reactions that are first-order with respect to the reactant. Further properties of first-order reaction kinetics. The integrated first-order rate law is usually written in the form of the exponential decay equation. A different way of considering first-order kinetics is as follows. The exponential decay equation can be rewritten as where corresponds to a specific time period and as an integer corresponding to the number of time periods. At the end of each time period, the fraction of the reactant population remaining relative to the amount present at the start of the time period will be such that after time periods, the fraction of the original reactant population will be where corresponds to the fraction of the reactant population that will break down in each time period. This equation indicates that the fraction of the total amount of reactant population that will break down in each time period is independent of the initial amount present, when the chosen time period corresponds to the fraction of the population that will break down in each time period will be exactly 1/2 the amount present at the start of the time period. The average rate of the reaction for the nth time period is given by. Therefore, the amount remaining at the end of each time period will be related to the average rate of that time period and the reactant population at the start of the time period by. Since the fraction of the reactant population that will break down in each time period can be expressed as the amount of reactant that will break down in each time period can be related to the average rate over that time period by, such that the amount that remains at the end of each time period will be related to the amount present at the start of the time period according to. This equation is a recursion allowing for the calculation of the amount present after any number of time periods, without need of the rate constant, provided that the average rate for each time period is known. Second-order reactions. A second-order reaction depends on the concentrations of one second-order reactant, or two first-order reactants. Its reaction rate is given by, or this last equation stems from the definition of a rate law, with respect to a reactant. Consider the reaction 2A to B having a second-order reaction involving one reagent only must mean, in terms of the definition of a rate law, that the derivative of B with respect to time is equal to 1/2 of the derivative of A with respect to time. This is because for each B that appears, 2 as a disappearing. Thus, the speed with which A disappears is twice the speed with which B appears, because A is disappearing in groups of 2 while B is appearing in groups of 1. So, the derivative of B with respect to time is equal to -1/2 the derivative of A with respect to the time, taking into account the definition of the rate equation, which is a relationship between the rate of reaction in terms of the concentration of a given reagent. We can say that R equals A squared. If we were to make both expressions equivalent, we find that, thus, the derivative of A with respect to time must be halved to obtain the rate at which A is disappearing. The integrated second-order rate laws are, respectively, or A 0 and B 0 must be different to obtain that integrated equation. The half-life equation for a second-order reaction dependent on one second-order reactant is, for such a reaction, the half-life progressively doubles as the concentration of the reactant falls to half its initial value. Another way to present the above rate laws is to take the log of both sides. Examples of a second-order reaction. Pseudo first-order. Measuring a second-order reaction rate with reactants A and B can be problematic. The concentrations of the two reactants must be followed simultaneously, which is more difficult, or measure one of them and calculate the other as a difference, which is less precise. A common solution for that problem is the pseudo first-order approximation. If the concentration of one of a reactants remains constant because it is supplied in great excess, its concentration can be absorbed within the rate constant, obtaining a pseudo first-order reaction constant, because in fact, it depends on the concentration of only one reactant. If, for example, B remains constant, then, wherein an expression is obtained identical to the first-order expression above. One way to obtain a pseudo first-order reaction is to use a large excess of one of the reactants would work for the previous example, so that, as the reaction progresses, only a small amount of the reactant is consumed, and its concentration can be considered to stay constant. By collecting for many reactions with different concentrations of B, A plot of versus B gives us the slope. Example: the hydrolysis of esters by dilute mineral acids follows pseudo first-order kinetics where the concentration of water is present in large excess. CH3COO CH3 plus H2O CH3COOH plus CH3OH. Summary for reaction orders 0, 1, 2, and n. Elementary reaction steps with order 3 are rare and unlikely to occur. However, overall reactions composed of several elementary steps can, of course, be of any order, where m stands for concentration in molarity, T for time, and K for the reaction rate constant. The half-life of a first-order reaction is often expressed as T1/2 equals 0.693 K. Equilibrium reactions or opposed reactions. A pair of forward and reverse reactions may define an equilibrium process. For example, A and B react into X and Y and vice versa. The reaction rate expression for the above reactions can be expressed as where K1 is the rate coefficient for the reaction that consumes A and B, K2 is the rate coefficient for the backwards reaction, which consumes X and Y and produces A and B. The constants K1 and K2 are related to the equilibrium coefficient for the reaction by the following relationship. Simple example: in a simple equilibrium between two species, where the reaction starts with an initial concentration of A, with an initial concentration of 0 for B at time t equals 0, then the constant K at equilibrium is expressed as where and other concentrations of A and B at equilibrium, respectively. The concentration of A at time t is related to the concentration of B at time t by the equilibrium reaction equation. Note that the term is not present because, in this simple example, the initial concentration of B is 0. This applies even when time t is at infinity, i.e., equilibrium has been reached. Then it follows, by the definition of K, that therefore, these equations allow us to uncouple the system of differential equations, and allow us to solve for the concentration of A alone. The reaction equation, given previously as the derivative, is negative because this is the rate of the reaction going from A to B, and therefore the concentration of A is decreasing. To simplify annotation, let X be the concentration of A at time t. Let B the concentration of A at equilibrium. Then, since the reaction rate becomes, which results in a plot of the negative natural logarithm of the concentration of A in time minus the concentration at equilibrium versus time t, gives a straight line, with slope kf plus kb. By measurement of A and B, the values of K and the two reaction rate constants will be known. Generalization of simple example: if the concentration at the time t equals 0 is different from above, the simplifications above are invalid, and a system of differential equations must be solved. However, this system can also be solved exactly to yield the following generalized expressions. When the equilibrium constant is close to unity and the reaction rate very fast, for instance in conformational analysis of molecules. Other methods are required for the determination of rate constants, for instance by complete line shape analysis in NMR spectroscopy. Consecutive reactions. If the rate constants for the following reaction are then the rate equation is for reactant A, for reactant B, for product C, with the individual concentrations scaled by the total population of reactants to become probabilities. Linear systems of differential equations such as these can be formulated as a master equation. The differential equations can be solved analytically, and the integrated rate equations of the steady-state approximation leads to very similar results in an easier way. Parallel or competitive reactions. When a substance reacts simultaneously to give two different products, a parallel or competitive reaction is said to take place. Two first-order reactions, and with constants and rate equations, and the integrated rate equations are then, and. One important relationship in this case is one first-order and one second-order reaction. This can be the case when studying a bimolecular reaction and a simultaneous hydrolysis takes place. The hydrolysis complicates the study of the reaction kinetics, because some reactant is being spent in a parallel reaction. For example, A reacts with R to give R product C, but meanwhile the hydrolysis reaction takes away an amount of A to give B, A byproduct, and the rate equations are and, whereas the pseudo first-order constant, the integrated rate equation for the main product, C, is, which is equivalent to, concentration of B is related to that of C through the integrated equations were analytically obtained, but during the process it was assumed that, therefore, previous equation for C can only be used for low concentrations of C compared to zero stoichiometric reaction networks. The most general description of a chemical reaction network considers a number of distinct chemical species reacting via reactions. The chemical equation of the TH reaction can then be written in the generic form, which is often written in the equivalent form. Here is the reaction index running from 1 to denotes the TH chemical species, is the rate constant of the TH reaction, and are the stoichiometric coefficients of reactants and products, respectively. The rate of such reaction can be inferred by the law of mass action, which denotes the flux of molecules per unit time and unit volume. Here is the vector of concentrations. Note that this definition includes the elementary reactions, zero-order reactions, for all first-order reactions, for a single second-order reactions, for exactly two, i.e., a bimolecular reaction, or for a single, i.e., a dimerization reaction, each of which are discussed in detail below. One can define the stoichiometric matrix denoting the net extent of molecules in reaction. The reaction rate equations can then be written in the general form. Note that this is the product of the stoichiometric matrix and the vector of reaction rate functions. Particular simple solutions exist in equilibrium, for systems composed of merely reversible reactions. In this case the rate of the forward and backward reactions are equal, a principle called detailed balance. Note that detailed balance is a property of the stoichiometric matrix alone and does not depend on the particular form of the rate functions. All other cases where detailed balance is violated are commonly studied by flux balance analysis, which has been developed to understand metabolic pathways. General dynamics of unimolecular conversion. For a general unimolecular reaction involving interconversion of different species, whose concentrations at time are denoted by through an analytic form for the time evolution of the species can be found. Let the rate constant of conversion from species to species be denoted as, and construct a rate constant matrix whose entries are the. Also, let be the vector of concentrations as a function of time. Let be the vector of ones. Let be the times identity matrix. Let be the function that takes a vector and constructs a diagonal matrix whose on-diagonal entries are those of the vector. Let be the inverse Laplace transform from 2. Then the time of old state is given by, thus providing the relation between the initial conditions of the system and its state at time.